Josh Speagle is a PhD student here at Harvard and previously was a researcher at the Kavli Institute for the Physics and Mathematics of the Universe. I don't usually quote from people's websites directly, but this description of what he did was so cool. I just had to quote it verbatim, or quasi verbatim. He worked on improving the photometric redshifts for the Hyper Subprime Cam Subaru Strategic Program survey, funded by a CREST grant from the Japan Science and Technology Agency. Just one of the coolest sounding descriptions I've ever heard. Although I admit I'm not completely up on what all of the different components are. Before Kavli, he completed his bachelor's degree here at Harvard, where he was funded by both the Herschel Smith Undergraduate Science Fellowship, which is essentially our most prestigious summer research fellowship, as well as the Harvard College Research Program. He held a Weizmann International Internship Program Fellowship and received a Chambliss Astronomy Achievement Student Award, and has quite a large number of papers, including the X-ray counterpart of the high-B pulsar J07262612, which I think you published as a freshman in college?
Yeah.
Not bad. He's going to tell us about the Milky Way's Dust-iny. Let's all welcome Josh.
Thanks a lot for the introduction. I really appreciate it. So I actually primarily work on galaxy evolution and cosmology, so studying the evolution of the universe. With Daniel Eisenstein here at the astronomy department. I'll be starting my third year in 2 weeks or so. But today I'll be talking about sort of a side project that I started a few months ago with two other research groups here at the Center for Astrophysics and the astronomy department. The first is sort of the DUST group headed by Doug Finkbeiner, who I think actually talked here a couple years ago. And some of the postdocs he's worked with, Greg Green, Eddie Schlafly, who were previously students here, and a graduate student, Catherine Zucker. In a collaboration, I've tried to strike up with a group that studies stellar evolution, in particular helping to improve stellar modeling. And so that includes Charlie Conroy, two of his postdocs, Phil Cargyle, Ben Johnson, and Rohan, another graduate student. So today I'll talk about, hopefully I'll convince you that dust, even though it might be a pain, is pretty exciting and actually quite cool. So the first thing I want to do is just back up and say, what do I mean when I'm saying dust, right? Why am I talking about dust in the galaxy? And so I think the standard thing that you might say is, well, research is hard. Observing things is hard, experiments are hard. Anyone you talk to can affirm how much of a pain it is to actually do real science. And so for astronomers, that primarily means that you want to build a giant, telescope, put a huge piece of glass on some huge robot, and then point up at the sky and try and study whatever it is you're looking at. And this is challenging, of course, because you always have instrumental effects, right? Your telescopes are not perfect. There are always things involved with data reduction. So hopefully you have some really good engineers and programmers who can design software and different electronics to help deal with this. But even if you design the perfect telescope and you know exactly how it works, the real problem is Earth itself. The atmosphere sort of impedes any observation we want to make of space. And that's primarily because the atmosphere contains lots of nuisance molecules like water and oxygen that get in the way of observing a nice clean space air, and also have air which has a lot of turbulence and heat, so wind patterns, convection, and et cetera, essentially blur out lots of the images. And so some astronomers, or at least the non-zero number, have this dream that one day the atmosphere of the Earth will be evacuated, and in that glorious moment, before we all perish, the sky will be beautiful and uninterrupted. But the alternate to that is paying a lot of money and sending up telescopes into space with a rocket. But even if you do that and you escape the Earth, you're still stuck with what's known as the interstellar medium, which is a fancy term for everything that's between stars, interstellar, between you and whatever you're trying to observe. So this is just a bunch of stuff in space naturally that's not, essentially stars and planets. So this is between, all the stuff in between all the things that most people care about. The interstellar medium is everywhere. It's primarily composed of gas. About 99% of it is, some version of hydrogen. But about 1% of it is dust molecules. And these include a variety of things like graphites, so the same type of stuff in your pencils, silicates like sand, as well as sort of ices and other types of hydrocarbons, And although it only makes up about 1% of the interstellar medium, it actually scatters 30% of all the light that's emitted in the universe. And so that's a huge problem because this dust is everywhere. This is just an image of the Milky Way, so projected, of course, onto a flat surface. So this is, again, in longitude, latitude, and galactic coordinates, taken by the Planck team, a satellite launched by the European Space Agency. And so this map is in logarithmic scale, so darker regions indicate that there's orders of magnitude more dust in the way than these brighter regions. And so essentially, if you're trying to observe anything in the galaxy or even outside of the galaxy, you're going to be looking through some amount of dust. You can't get away from it. So trying to understand what exactly this is crucial to doing good science. In addition, dust is formed by lots of stellar processes. So in stellar evolution and also in supernovae, you form lots of these more complex dust molecules. And so by actually studying the chemical composition and location of these of dust, you can actually learn about the evolution of the Milky Way. And so I just want to point out that, for example, lots of these features are real. So some of them are stretching artifacts the same way that you see them on like a map of the Earth. But many of them are actually real features that tell you something about how the Milky Way has evolved over time. So what this means in practice is that when we're interested in looking at something, like let's say a star, and we're here, we have the nice eyeball representing us. Stars are emitting light at all sorts of wavelengths. They emit all the way from the ultraviolet to the infrared. And in the way, they're going to be blocked by these dust molecules, which are about 0.1 microns or so in size. So about 10 to the negative 7 meters or so. And what this means is that dust has two effects on the light that we observe. The first is that it's just blocking a bunch of light. So light comes in, dust is going to block it and absorb some of that light, and it's going to re-radiate it in the very far infrared. And so that means that it's actually going to do what we call extinction, which is that whatever light comes in, it's going to block some of it, and so the light that we see is going to be fainter. We're going to see less of it. The second thing is that this type of blockage is wavelength dependent. Dust is more likely to scatter, essentially light with shorter wavelengths, or light that's bluer. And so as bluer light comes in, it's going to be preferentially scattered in directions away from us. And so we will see even less of the blue light than the red light. And so this phenomenon means that relative to its original sort of color, an object is going to look redder, or in this case, de-blued, because you're removing blue light but keeping more red light. And so that means that you're going to end up with a spectrum or any type of colors that you're looking at of a star that is redder than it originally was and also fainter. What this looks like in practice is sort of shown here. This is an example of a spectrum. So on the x-axis, we have wavelength in angstroms, so 10 to the negative 10 meters. The wavelengths of visible light are sort of in this region. So this is on the x-axis. This is all in log scale. The y-axis is the relative intensity as a function of wavelength. And so this is just an example for a galaxy. And what happens when you impose dust in the way is you get something that looks like this. So you're losing a lot more of light that is bluer with shorter wavelengths than light that's redder. And so ultimately, you're going to end up with something that is relatively redder than what you started with. So over the course of many years, so about 20 years ago, you can measure a bunch of different stars in regions where you think that there aren't a lot of dust, or you think you know what that dust is doing. And you can collect all this to sort of, on aggregate, say what dust looks like in the Milky Way. How is it affecting our observations? This ends up being what's called an extinction curve, or essentially the relative amount of light that dust blocks as a function of wavelength. And so astronomers have this terrible tendency of having obscure units for everything and plotting everything backwards, and this plot is no exception. So blue is actually going to the right, and red is going to the left, and the units are in inverse wavelengths. So it goes towards infinity at 0. And the y-axis is also in terms of more extinction, so more light is being blocked as you go up, and it's in logarithmic units too, with some weird factor in front. So the takeaway here is that this is sort of the average shape of what dust is doing in the Milky Way in terms of blocking our observations of stars. And so you can see that more light relative to some places being blocked in the bluer wavelengths versus the redder wavelengths. But we think that we understand sort of broadly how this is working, even if we don't necessarily know exactly what dust is made of. So this is an entirely empirical measurement. We've just looked at, in this case, Ed Fitzpatrick looked at about 100, 150 stars and tried to sort of average out what he thought was going on. So this is a nice view, and if our data was all this nice, we would be done. But unfortunately, large data sets in astronomy are never this pretty, and I'm sure large data sets in general are never this pretty. The big problem here is that data like the one I showed you, where you're able to really estimate this effect as across all different wavelengths, is an example of a spectrum, where you can measure the intensity of light as a function of wavelength for a bunch of different objects. So this is another example of a galaxy. All these features are actually real, caused by certain atomic and molecular transitions. These are really expensive and slow. You have to take your light, you have to put it through some type of prism or grism to split it up into all these different colors and then measure it on some instruments. So you really have to go at objects, one at a time or maybe a group at a time. What's much cheaper is just taking a picture. Is you have these giant cameras, you can just point them at the sky and just see what you get. And so that's known as photometry. And so here's an example of what one of those images look like. This is actually taken from the Hyper Supreme Cam survey that Scott was mentioning earlier that I've done work on. And so this is a false color image taken in a couple different filters. Slightly different from the Instagram filters, but similar idea. And so all that we've done is essentially we put these different filters on. These are known as broadband filters, so they cover some wavelength range. We essentially just take a picture in that filter and add up all the light that comes in. And so these little dots indicate essentially how much light we observe for any particular object. And so by combining them, you can make images like this, where these different colors indicate essentially different amounts of light in each of these different filters. So what this gives us is what's known as a really rough spectral energy distribution, or SED. And so that's just shown here is the size indicates sort of how much light we're getting, and the color indicates sort of what wavelength range we're probing. So this gives us a very rough idea of what galaxies and stars are doing. So this is the data we have to work with. And so we have to think of what exactly is dust doing in this data set, how can we study it? And the issue comes in when if you want to know, for example, what this tiny red object in the upper right, on the upper corner of this figure is doing, we have no idea what that is. It's just a blob on the image with a set of colors. So is that a star? Is that a galaxy? How much dust is in front of it? We really have no idea. We have to somehow model every single blob in this image to really get out the really physical, interesting astrophysics that we care about. So this is a little hard. If we knew what every star looked like or every galaxy looked like, this would be pretty straightforward. We'd say, okay, this is what we expect. This is what we observe. The difference must be due to dust. But stars actually are not all the same, unfortunately. So our sun is one example, but there are stars that are smaller and also bigger. And they also evolve during their lifetime. As Laura mentioned, for instance, the sun was fainter a few billion years ago by about 30%. And so we really have to take all of this into account when we're looking at a certain blob. And so one example of what this looks like is by taking sort of a cross-sectional view. And so if we take a snapshot of 1 million stars, which is what's shown here, this is some work from Greg Green, and we just put them on a picture, what's shown in these series of plots is what's known as color-color distributions. So each of these axes is essentially a ratio of, say, like blue versus green or green versus red. And so the relative colors of each of these stars changes. So this is taking 1 million stars and asking what does the colors of all those stars look like. And it turns out that colors actually occupy a very specific locus in this type of color space. So there is, as stars change, as you have smaller stars and bigger stars, they have systematically different colors. And so that's really helpful in one way, because that means that when we're out looking at something, stars actually do behave in a really consistent way. We can sort of understand, these are like lower mass stars, these are higher mass stars, for instance. And over the course of a star's lifetime, they're sort of going to jitter around a little bit, for the most part, in some region of this diagram. The issue is that the effect of dust is really, really insidious on this diagram. And so when I showed you sort of the effects of dust before, now, in this sort of view of all these different colors, dust has the effect of introducing what's known as this reddening vector. So it moves the colors of stars in a very particular way on this diagram. And so that's indicated by the arrows in each of these plots. And unfortunately, you can see these arrows pretty much line up with what stars are actually doing. And so this means that dust can can essentially take a star that looks like it's at higher mass or lower mass and put it in a different position. So it can fool us. In addition, because dust is blocking light, it also means that we think the star is further away. Because stars that are further away, generally we get less of their light on Earth. And so dust has this effect of introducing this double degeneracy, where stars that are large and bluer and dusty and far away can be sort of confused with stars that are small, dust-free or clear, and close by. And so this means that you end up with some really pathological behavior, and this is sort of true because of a lot of physics and not because of sort of the specific choice of colors that we're looking at. Dust tends to have this effect all over the place. So this is sort of the conundrum, is how, if we have all these blobs, when we look at data like this, assuming that we can reduce this data to stuff that we can model and use, which is a hard problem, but not one that I'll talk about today, how can we actually go about modeling this? So how can we figure out, for example, what type of star this is, how far away it is, how much dust it has in front of it, et cetera. So the basic approach for this is relatively straightforward in theory. So we're just going to go sort of the standard Bayes theorem right away. We are interested in trying to simultaneously model some properties of the star, which I'll call theta, some measurement of the reddening, assuming that we know, what the dust is doing, which I'll call r, and then some measurement of the distance, which we'll call d, because we have to model all those at the same time, conditioned on our measurements. And that's going to be proportional to, some prior and some likelihood that we're looking at. So each of these two terms, our prior, it has to encompass all the knowledge we know about how stars are distributed in the galaxy. And so this means that we have to specify some type of galactic model where we think stars are, the distribution of stars in the Milky Way, what properties they have, how massive are they, what's their chemical composition, how does that vary as you go in different places in the galaxy, and also what's the dust doing at different places as well. So we have to come up with some guess for what we think these are, for most of the Milky Way. This is challenging, but we can draw on sort of a reasonable set of literature to come up with a good starting point, right? That's always what a prior is meant to be, as a starting point for your analysis. The likelihood we're going to be using is going to be Gaussian. So we're going to assume our data really is, we're going to take a Gaussian approximation. It's fundamentally Poisson noise. We're counting up sort of the amount of photons or light particles that our telescopes observe. But since we're often working the limit where we're dealing with thousands of these, we can take a Gaussian approximation for this. Our model then we're going to assume is either perfectly known or has some small Gaussian errors that we can add in to either regularize our results, or if you're thinking of like a Gaussian process or something, this would be something like the variance, the uncertainties in our models. So this is in theory. In practice, this is really challenging. The first is that, as you might imagine, stars are really complicated. And so coming up with these stellar models is really computationally intensive, and from scratch really involves like supercomputer time. You have to solve a bunch of very difficult equations like radiative transfer, chemical evolution, nuclear fusion, to really get a sense of what stars are doing, at any point in their lifetime. So that's not really feasible for us. So we have to find some way around having to do that sort of on demand. The second is, as mentioned before, is that the parameter space is multimodal. So fundamentally, we have these really pathological degeneracies that make this problem really resistant to methods that scale really well to big data sets. So MCMC methods generally fail when you have these widely separated modes. Variational inference has a lot of problems when you have these multiple solutions. And so we have to come up with some sampling method or some computational approaches to really make this tractable for us. And so just to give an example of what this looks like, here is an example, a snapshot of a handful of stars. The y-axis here is reddening or extinction, again in log units. The x-axis is distance in log units, using a set of models that we have from some work that Catherine's been doing. And you can see sort of how pathological these probability distribution functions really look. And so you can see that often they're multimodal, they have these curving degeneracies, and these are often due to the fact that in the Milky Way, because the Earth is situated inside the actual galaxy itself, when we're looking through the galaxy, there are often symmetrical solutions to our problem. So the star could either be close by, or maybe it's on the other side on a different galactic arm, and it would be in the same position. This is true for a wide variety of different line of sights that we can have, and so this introduces all these different, possible doublets, essentially, of star positions, or in some case, triplets. So this is really difficult. So somehow we have to be able to derive these individual probability distributions where for each star we don't really know its distance and reddening, but can sort of constrain them in a statistical sense. The way that the first approach that the group used to do this was to throw out essentially the use of theoretical stellar models. These were way too intensive. They wanted something that was simpler. And so they constructed a set of really crude empirical models from some data that I'll discuss in a little bit. And so that actually allowed them to, what this did is nice, and it has an upside and a downside. The upside is that this allowed them to really go after this problem quickly, right? It's sort of, but on the downside, it means that we lose access to all the physical properties of stars that we care about. So we're really treating this as a nuisance parameter at this point. So by using these empirical models, you essentially can approach this problem in a much more computationally tractable way, but you lose all the interesting stellar physics that we might care about. So I'll get back to that at the end of the talk. The second is that there are a bunch of different ways to probe this multimodal space. One thing I've been really interested in is nested sampling and other types of more flexible approaches to dealing with these problems. But ultimately for this particular application, we found that it was faster to use essentially a sort of combined version of a brute force approach over the stellar properties, combined with linear optimization and Monte Carlo integration over the distances and reddenings here. And so that's just exploiting a lot of nice properties of multivariate Gaussian distributions and et cetera, which I can talk about in more detail if you're interested. So this is sort of for the individual stars. The next step, if we want to actually create a dust map, is to take advantage of essentially correlations along the line of sight. And this is just taking some very basic physical principles, which is if you look in one direction straight, dust can only increase along that direction, right? You can, at no point can you have negative dust, where somehow something behind a given dust molecule or particle is going to negate the impact of that particular dust molecule. So you're always going to have more and more dust the further away you look in a particular direction. And so if you have many stars along this particular line of sight that have the same dust column in front of them, you can use those stars to constrain the cumulative amount of dust as a function of distance. So what this looks like, again, this is sort of reddening here, or dust, the amount of dust. This is distance, all in log units. And so over time, you can constrain sort of more and more of these. And so we can use our probabilistic estimates earlier to now constrain what this cumulative dust is doing along the line of sight. And this is what is ultimately going to give us a dust map. And so the way that we actually model this is, assuming that this loads, yes. Whoops. Can you actually play videos? Oops.
Linked to anything?
No, it's definitely connected, but it doesn't seem like it's playing. Let me just test the other one. All right, that at least seems to work. Okay, so it seems like the YouTube videos might not necessarily play, but essentially the punchline here is that what we're trying to do is we're trying to maximize the likelihood that's formed by integrating our line of sight through all of our individual stellar posteriors. And so by essentially taking all these different stars and asking, is this particular dust model consistent or maximally consistent with all these individual PDFs, we then arrive at sort of an optimal line of sight model. And so that's really the ingredients that we use to create, to ultimately create this. And so the next step is actually to go out and do it. And so these are sort of the ingredients for creating this dust map. The first is to take 800 million stars from the Pan-STARRS survey. So this is shown here. This plot is, again, another weird projection. So this is, the color is number density of stars. So this is the galactic plane. Each of these different holes and missing regions is due to the fact that if you have a telescope in Hawaii, you can't see through the Earth. And you also can't necessarily look too far up or down. So you take these 800 million stars. We're going to take the sky and we're going to divide it into all these different regions called pixels. And these are essentially just, a fancy way of saying we're going to assume the dust in each of these pixels is the same, so we can use stars along the line of sight to make these types of constraints. Then we farm all these 800 million stars out to a giant cluster, and kill our fair share score on the Odyssey computing cluster here. And ultimately, we're going to fit all the individual posteriors for each of these stars and the line of sight model at the same time. And so what this gives us is going to be posterior samples at the end. And so this work was originally done in 2015 and later updated in 2018, and has been really cool. So I want to show you a video now that's formed from this 3D map, which is available online. So this is a 3D tour around the sun. So you can see here that we're sort of looking at the galactic anticenter, so away from the galactic center. And this 3D map is entirely made with the data from this project. So these are all based on individual stars. You might notice that the map is a little bit choppy. That's because of sort of the pixelization effects that I just mentioned previously. Another way to look at this is to look at 2D slices of the map. So in other words, we're going to sweep through on the bottom. So this is going in distance. We're looking further and further away in the same direction. You can see different features of the Milky Way dust map sort of emerging at different distances. And so all these structures are actually distinct, and we can isolate them using all of this individual stellar data. You might notice that this map has a little bit of like jitter in it. So this is actually because for every frame, we're drawing individual samples from our chains for the line of sight model. And so this is a way of representing our uncertainty when we make these plots. But you can see that we're actually able to distinguish a bunch of these different particular regions on the sky. And this is all just using these really rough stellar data that we were looking to. So one of the things that we're really interested in looking forward is going to be how can we make this dust map better. So the original one that I showed you previously, like that was done 3 years ago. We updated it this year and last year. And so looking forward, we really want to say how can we leverage more data sets that have come in recently to make this map better. And one of the ways that we're doing is using a satellite called Gaia. So Gaia was launched by the European Space Agency recently, and it used a special effect known as parallax by looking for the small shift in stellar positions as the Earth orbits the sun, the same way that our eyes can detect small differences in position from a given, from where we're standing, to actually measure the distances and velocities of over 1 billion stars in the Milky Way. And so for us, this has been transformative because it's an independent constraint on the distance that's totally insensitive to our method, which relies on information about the stars. And so this is the same plot I showed earlier. So the y-axis again is reddening, and the x-axis is going to be distance. And so this is what we were looking at before Gaia, and this is what we get after Gaia. And so it's really amazing how well it can pin down the distances in cases where we have really good estimates for these stars, and in some cases it's able to help us distinguish between solutions that are multimodal. So it can give preference to one of the modes over the other, even if the data is not amazing. And so we're really looking forward to being able to incorporate this information into these estimates going forward. The second thing, and what I've been mostly involved with my tenure on the project, is trying to sort of reincorporate lots of improvements in stellar modeling into this approach. So as I mentioned, the first iterations of these projects used empirical models, which really treated stars as nuisance parameters to be sort of like ignored or marginalized over. And I've been really involved trying to go back and saying we care about the stars. As part of the dust, we want to learn things about these stars, what their masses are, what their chemical composition is, how old they are, and things like that. And so I've been using, with Charlie Conroy's group, improved stellar models from their libraries that they've been developing here. And so an example of what that looks like is shown on the right. So the y-axis is sort of brightness in log units. The x-axis is color in one particular ratio of bands. And each of these different stripes you can see is actually a different stellar mass. And each of these different dots shows how that particular star changes over time, over the course of its lifetime. The color in this diagram is a function of chemical composition, essentially going from regions that have very low elements that are heavier than hydrogen and helium, and to stars with a lot more of those. So you can see that just in this diagram that you're actually very sensitive to some of these changes in terms of what stars' colors are based on their age and their chemical composition. And so I don't want to show more complex plots here, but I've run a battery of tests on mock data and real data and have started incorporating this into the analysis pipeline we're using, and they look really promising. And so hopefully this will mean that no longer will we just be looking at dust maps in the Milky Way, but also sort of stellar maps, so we can actually see the histories and properties of all these individual stars. Some more speculative stuff that we're looking at I want to mention, because given that this is a big data conference and people here work on a variety of different analysis tools, this is the perfect opportunity to get feedback from all of you. One of the big things I've been looking forward to is trying to improve our modeling of dust along the line of sight. The current model has a reasonable number of issues. The biggest two are that it's optimized, so we're finding the best fit dust model given all of our individual stellar posteriors, and it's also discretized. So each of these different points here is fixed. So we've specified them ahead of time to give us sort of different bins in dust. One of the things that I've been really interested in is trying to turn this into more of a hierarchical approach, using hierarchical Bayes to simultaneously model both the dust along the line of sight and the individual stars, and also making this a more continuous process using things like Gaussian processes. So that, because ultimately we have constraints where we think we have stars, and we don't really have constraints where we don't. And we would like to incorporate that information and certainty when we make these types of maps. The final thing is trying to incorporate sky regularization. This is really just taking advantage of the fact that in our original analysis, each of these pixels we assumed was independent of each other when we're making these maps. And so that doesn't really show up when you look at these really big scale images like the Planck team shows here, but it does when you zoom in. You can see all these discontinuities across the sky. And so we're looking into trying to regularize this so we can create a map that's smoother and more physical, because dust does tend to trace each other. So when you're in neighboring pixels on the sky, probably should have similar amounts of dust, and we're trying to get it so that we can smooth some of that discontinuity out. So I just want to leave a set of final thoughts here, which is that the analysis code for these projects is public and online. So the original code Baystar and also the code I'm developing, Brutus, is on GitHub, and you guys are welcome to take a look. The dust map is public on the website argonaut.dustmaps.info, and you're more than encouraged to check it out. It's a really cool site. Greg did a fantastic job. And we're really excited to prepare for the next iteration of these maps and hopefully leverage these new surveys and new data sets, and also improve modeling to come up with a map that not only will be for dust, but also the entire Milky Way stellar history. So we're really excited for that. Thanks.
Really nice work, Josh. So you mentioned dust mostly as something that's annoying to us because it gets in the way of the stars and galaxies we want to observe. But these dust maps are beautiful, and I was wondering if there's information in there that is actually astrophysically useful about how stars have moved through the galaxy over time or something like that.
Yeah, so there is evidence for that. I mean, Doug can talk at much more length about this in particular, but by studying dust in the Milky Way is not uniform and does vary spatially. And so by studying those, you can learn about sort of the chemical evolution history of the Milky Way, for instance. Some of the features are very indicative of certain star-forming regions or evolution of certain clusters.
Can you see a supernova that went off, things like that? Or is it not?
The time scale of that is kind of hard, but definitely if you look at sort of star-forming regions, you can see the impact of, molecular clouds and these really active star-forming regions blowing away dust. So you can see lots of those physical impacts directly, yeah.
Cool.
So it's pretty cool, but that's primarily not what I study.
Okay, thanks.
Just kind of piggybacking on that, is there ever a concern, if a major event does happen, that it will sort of make your map out of date very quickly? And is there an easy way to get new information?
Yeah, so sort of quickly in astronomical terms is often really different from quickly in human terms. So most of the dust that are on these maps are really far away. And so while things are moving and evolving, they often take place on the scale of tens of thousands of years rather than sort of on the time scale of years. So for planetary studies, things actually can happen faster. And there are some pretty cool cases of disintegrating planets, for instance, that we've observed. But for dust, it's usually a little bit less of a concern. at least on like timescales that we care about. But yeah, like 10,000 years in the future, people might have to use a slightly updated dust map and stars might move. That's always a concern.
All right, let's thank Josh again. It was totally awesome.